Let's talk about forming covalent compounds. What compound is formed by hydrogen bonding with hydrogen? Now remember, we were just talking about ionic compounds, which means you should know that you have to have a metal and a non-metal in order for an ionic compound to form. But look at hydrogen. Hydrogen is classified as a non-metal, and as such, if you have a non-metal and a non-metal, they do not form an ionic bond. Because in order for an ionic bond to form, you have to have one atom lose an electron while another one gains it. How much sense does it make for this hydrogen to lose one while this one gains it? They're going to want that electron equally. And so because of that, they're going to share that electron. And what's formed? A covalent bond. Covalent bonds are simply sharing of electrons. So instead of one stealing and one accepting, one giving it up, you're going to have a covalent where they're going to share it. So in this case, you have a single bond forming. A single bond is 2 electrons. Anytime you have 2 electrons being shared, that is a single bond. These are other ways of representing hydrogen bonding. You have a line between 2 balls, or 2 balls that are just attached and you can't see the bonding. You can also have double bonds and triple bonds. So here you see oxygen with 2 lines between it, which means it's a double bond, and you have nitrogen with 3 lines between it, which means it's a triple bond. Now, covalent bonds are only between nonmetals. So if you have a metal in the compound, that means there is an ionic bond present. Covalent bonds need to be with nonmetal to nonmetal. Here are some examples of diatomic or polyatomic molecules. So there are 7 gases that exist diatomically, meaning hydrogen bound to itself, nitrogen bound to itself, etc. And what I think is really cool is 6 of those compounds form a 7 on the periodic table, as you see here in purple. And then hydrogen, it's always unusual, so it's up here. So you've got a 7 forming the 7 diatomic compounds. So if you ever hear iodine gas, it's not referring to I by itself. It's referring to I2. Same thing for the others. But then the word poly means many. So instead of di for 2, it's polyatomic. So many molecules bound together, but it's a molecule, not a compound, which means it's got just the molecules of the one atom type. Okay, so in this case we have a molecule of sulfur and a molecule of phosphorus. I want you to start out by looking at this list of compounds and figure out whether each one is either ionic or covalent, and then circle all of those that are covalent. So for instance, start out with nitrogen with 2 nitrogens and 5 oxygens. That has both nitrogen and oxygen in it. And so since nitrogen and oxygen are both non-metals, what kind of compound is that? Hopefully you said covalent. You would be correct. Okay. What about water? Water has hydrogen, non-metal, oxygen, non-metal. Therefore, it's going to be a covalent bond. What about sodium and chlorine? Sodium's over here, a metal. Chlorine over here, a non-metal. So therefore it is ionic. And just keep doing that until you've figured out whether each one is ionic or covalent. You should have circled all of these. These are all the covalent ones. Notice sucrose, which we've looked at before, has carbon, hydrogen, and oxygen in it. All 3 of those atoms are nonmetals. Therefore, that molecule is covalently bound together. Alright, so let's do a little review. We talked about how to name ionic compounds before. So stop the video and try and name each of them. Remember, you just say the name of the 2 elements, but then you replace the ending of the second element with "ide." So we have sodium chloride, magnesium oxide, aluminum fluoride, and lithium oxide. Hopefully you got all of those right. If you did not, you need to go back and review or ask questions. Now we're going to work on naming covalent compounds. So very similar to ionic compounds, but yet completely different. It's similar in the fact that every second element still ends with IDE, so it should end with "ide." But now you're going to use this table 4.4 that you see on the right, which includes the prefixes. So mono, if there's only one of the first atom, well, not actually the first atom, but if one atom means mono, di is 2, tri is 3, and so on and so forth. The only exception for that is for the first element you never use mono. For the second element you'll use mono. So what that means is for this first one you have 2 nitrogens, so that is di is the thing that means 2, so you have di-nitrogen, and there's 5 oxygens. So you find on the list 5 is penta. So it should be dinitrogen pentaoxide. But oxygen's a strange one, so we will replace the penta with an O, pentoxide. So it's dinitrogen pentoxide. Now water. You have 2 hydrogens, so dihydrogen monoxide, dihydrogen monoxide. Try the rest on your own. You should get dichlorine heptaoxide. Number 4, carbon dioxide. Number 5, sulfur trioxide. Number 6, carbon tetrachloride. And then number 7, phosphorus tribromide. So look at those, figure out if you have any questions, and figure out why they were named as they were. So remember, you've got your prefixes, and then your ending is an IDE. Now I'm going to show you these same compounds again, so hide your list if you took notes, and I want you to try and fix the names that are on here. So I'm going to give you incorrect names, and I want you to try and fix it. So with this one, for instance, dinitrogen pentaoxide. Remember, oxygen's a strange one, so you're going to remove the A and turn it to a pentoxide. Number 2, hydrogen monoxide. It forgets the di in front of the hydrogen. This one, dichlorine heptaoxygen. So with this one, dichlorine heptaoxygen. Hopefully you see that the gen should be oxide. This one, monocarbon dioxide. It looks right from a get-go, but remember you don't use mono in front of the first element. Sulfur trioxygen should be sulfur trioxide. And then monocarbon tetrachloride. Remember, mono doesn't belong on the first element. And then this last one, phosphorus 3-bromide. Phosphorus can only have one ionic form, so it doesn't need the Roman numerals. It should just be phosphorus tribromide. Alright, hopefully you did very well on that. So now we're going to switch gears a little bit and talk about polarity. So as we're thinking about covalent compounds, we're asking the question, I know they're sharing those electrons, but are they sharing that equally? Electronegativity is sort of like these people you see over here sharing a bed. You've got the one that really wants the covers, and you have the other that does not, and so they're freezing. Well, that's how it is with electrons. Some elements really want the electrons, and others don't really care, to be honest. And so with electronegativity, you're never going to have a complete, perfect sharing of electrons unless it's nonpolar. If your electrons are shared unequally, even in the slightest, then it's going to be considered polar. And so we're going to look at some compounds and figuring out whether or not they are polar. So just to give you a numerical basis behind electronegativity, fluorine is the most electronegative atom. And so if you look up at fluorine, it has an electronegativity value of 4.0. Compare that with like potassium. Fluorine really wants electrons. Potassium, it's going to turn into a +1, so it's super happy giving up electrons. So electronegativity is going to tell you who's going to hog the electrons in their relationship. And in this case, the closer you are to the top right-hand corner of the periodic table, with fluorine being the top right, the more you're going to want the electrons. All right. In addition to that, if you subtract, so let's say fluorine and hydrogen are bound together. If you take fluorine and you subtract hydrogen score, you're going to get 1.9, which means it is going to be a polar covalent bond. And so when you're looking at these different values, you can just subtract them and find what's called your change in electronegativity, or a delta symbol, and you're going to be able to tell what type of bond it is, a nonpolar, polar, or ionic. So let's give some examples here. So if hydrogen bonds to hydrogen, is it a nonpolar covalent, polar covalent, or ionic? Hopefully you're able to look and see that the two hydrogens have the exact same electronegativity value. Therefore the electronegativity difference is 0. This means the bond would be nonpolar, but it's still a covalent bond. It's not ionic. What about carbon and fluorine? If you look at carbon here and fluorine here, you have about a 1.5 electronegativity difference. That means the bond is a polar covalent bond. What about carbon and hydrogen? That's a much smaller difference there of only 0.4, which means this is a non-polar covalent, which means even though it is slightly going to be polar, it's all kind of a scale. Those breaks that we have of 0.5 and 2, those are kind of just picked by the textbook. I've seen different textbooks with different values. Really, it's kind of a scale of this one's more covalent than this one, unless it's 0, and then it's 100% non-polar covalent. Alright, so then for D, carbon with oxygen, that is a difference of about 1.0, which means that bond is polar covalent. So once again, when we're comparing these, all we're doing is we're comparing them with this chart that you see here, table 4.3. Alright, then for the last one, the electronegativity difference is 2.7 between potassium and oxygen, which means that bond is ionic. And if you had to figure that out, you knew that it would be because potassium is a metal, it's on the left side of the periodic table, and oxygen here is a nonmetal on the right. So you would expect that to be an ionic compound. Alright, so now I want you to do it again. I want you to classify each of these bonds as either nonpolar covalent, polar covalent, or ionic. Go ahead and stop the video. Write down what you think it is, and then restart it. You should have gotten for A, an electronegativity difference of 0.7, making it polar covalent. B, 2.6, making it ionic. C, 0.0, therefore a nonpolar covalent bond. And then D, 2.0, making it a polar covalent bond. Let's go a little bit different. Let's try this time to instead rank each of these bonds in terms of polarity. So meaning which of these 4 pairs has the largest electronegativity difference and therefore the largest polarity difference. Alright, so stop the video, try and figure it out, and then restart it. So A is 1, B is 0.5, C is 2.2, and D is 1.5. That means that the smallest electronegativity, that of a nonpolar covalent compound, or close to that, is going to be nitrogen and oxygen, then carbon and oxygen, then arsenic and oxygen, and then last silicon and fluoride. Alright, so now you've worked on learning about these covalent differences in polarity. Go practice and then go read sections 4.8 to 4.9.